In the last video, we discussed some general features that apply to all types of waves. Many waves we encounter must travel through a medium, such as water or air. Any wave that travels through matter is called a mechanical wave. However, there's another type of wave that needs no matter to transmit its energy, called electromagnetic waves. Radiation from the sun is an example of an electromagnetic wave, and that's the topic of this video. Electromagnetic waves are composed of alternating electric and magnetic fields. That's where they get their name. Like mechanical waves, electromagnetic waves have a frequency and a wavelength. But there are two remarkable differences. The first, as mentioned, is that electromagnetic waves travel through a vacuum. They do not need a medium through which to transfer their energy. They travel through empty space. The other interesting difference is that electromagnetic waves only travel at one speed, and that speed is the speed of light. Visible light is one form of electromagnetic waves, or electromagnetic radiation. Other forms include radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. So what do these different types of electromagnetic radiations, or EM, have in common, and how are they different? Well, they all travel at the same speed, the speed of light. We use the letter c to designate this known speed, which is 300 million meters per second. Using scientific notation, that is 3 times 10 to the 8th meters per second. The other thing they have in common is that they are all created by vibrating or changing electric fields. The thing that causes an electric field to vibrate or change will be discussed in the next math lesson. But for right now, it's interesting to understand what happens when an electric field changes in intensity. The blue arrows here represent an electric field vibration. As the electric field changes its intensity, it creates a magnetic field vibration in a perpendicular direction, represented by the red arrows. The crazy thing is that the changing magnetic field causes another changing electric field perpendicular to it, more blue arrows, which causes another magnetic field to vibrate, and so on, which keeps alternating from magnetic to electric until it is stopped by hitting something. These vibrating electric and magnetic fields travel through space in an electromagnetic wave at the speed of light. What distinguishes between different types of electromagnetic waves is the frequency at which they vibrate. The higher the frequency, the more energy in the vibrating electromagnetic wave. In fact, the energy of an electromagnetic wave is directly proportional to its frequency. So energy over frequency is a constant. Therefore, if the frequency of an electromagnetic wave doubles, so does its energy. The lowest energy electromagnetic waves are radio waves. These waves are the ones that are received by your radio coming from radio stations. If you check your radio dial, you can read the frequencies at which your radio station is set. For AM stations, the frequencies are in the thousands of hertz, or cycles per second. The lowest end of the dial is set to receive a frequency of about 540 kilohertz. That's 540,000 hertz, while the upper end of the AM dial is set to receive about 1600 kilohertz. FM radio frequencies are millions of hertz. The low end of the FM dial goes from about 88 million hertz to 108 million hertz. The term we use to indicate a million is mega, which is abbreviated with a capital M. So the FM dial goes from 88 megahertz to 108 megahertz. But electromagnetic frequencies can be much greater than millions of hertz. Electromagnetic radiation that vibrates billions of times per second are called microwaves. These are the waves created in a microwave oven, and are the waves that are used by cell phones. Microwave frequencies can range from about 1 billion hertz to about 300 billion hertz. The prefix giga means billion, so the highest microwave frequency is 300 gigahertz. As we increase the frequency, and thus the energy, of electromagnetic radiation, we move from microwaves to infrared waves. Infra means below, so infrared waves have frequencies just below red light. Infrared frequencies are produced by the motion of molecules in matter. The motion of molecules in matter is what determines its temperature. So as the temperature of matter rises, it gives off infrared electromagnetic radiation. As mentioned above, the frequencies of infrared radiation are just a bit lower than the frequencies of red light. This implies that visible light is actually just another form of electromagnetic radiation. And indeed, that's exactly what visible light is. Red light contains the least amount of energy of all the colors, because its frequency is the lowest of all visible light. Its frequency is about 430,000 gigahertz. As mentioned, the prefix giga means a billion, but there is another prefix, tera, which means a trillion. Since a trillion is 1,000 billion, we can say that the frequency of red light is 430 terahertz, or 430 trillion cycles per second. The next color in the visible spectrum is orange, at about 500 terahertz, then yellow, green, blue, and violet, which has a frequency of about 700 terahertz. After violet comes ultraviolet light, which has a frequency of about 1,000 terahertz. At these frequencies, electromagnetic radiation becomes dangerous to humans. Ultraviolet radiation can damage skin to the point of causing its cells to mutate into cancer cells. So far, we have listed ultraviolet as the highest frequency electromagnetic radiation, but there are two other types which are even higher, named X-rays and gamma rays. X-rays and gamma rays have frequencies in the millions of terahertz range. These frequencies are so high that they can penetrate through our body and have potential to mutate cells as they strike the DNA that make up our genes. Luckily, the Earth's ozone layer blocks these forms of high-energy radiation coming from the sun. As with all waves, electromagnetic waves not only have a frequency, but also a wavelength. And since the speed of all electromagnetic radiation is constant, about 300 million meters per second, it is not difficult to calculate the wavelength of any electromagnetic wave if we know its frequency. That's because, as we learned in the previous math video, the speed of a wave can be calculated by multiplying the frequency times its wavelength. Let's calculate the wavelength of a local Boston AM radio station, WBZ, which has a transmission frequency of 1030 kilohertz. Using scientific notation, we can write that as 1.03 times 10 to the 6th hertz. The speed of light in scientific notation is 3 times 10 to the 8th meters per second. So filling in our equation, C equals frequency times wavelength, we write 3 times 10 to the 8th meters per second equals 1.03 times 10 to the 6th hertz times lambda. To calculate the wavelength lambda, we divide C by F. So lambda equals 3 times 10 to the 8th meters per second over 1.03 times 10 to the 6th hertz. Remember, hertz is cycles per second, so we can see that seconds cancel out, giving about 2.9 times 10 to the second meters per cycle, or about 290 meters. So one wavelength of the radio wave radiating from that radio station is about the same length as 3 football fields. Let's compare that to the wavelength of an average microwave, with a frequency of 100 billion cycles per second, or 100 gigahertz. 100 gigahertz can be written as 100 times 10 to the 9th hertz, or 1 times 10 to the 11th hertz. We still have C as 3 times 10 to the 8th meters per second. So 3 times 10 to the 8th meters per second equals 10 to the 11th hertz times lambda. So lambda equals 3 times 10 to the 8th meters per second over 10 to the 11th cycles per second. And that gives 3 times 10 to the negative 3rd meters per cycle. That's 3,000ths of a meter, or 3 millimeters, much smaller than an AM radio wave. It makes sense that a microwave would have a wavelength smaller than a radio wave, because as frequency increases, wavelength decreases. At higher frequencies, you find even smaller wavelengths. An average ultraviolet wavelength is only about 100 billionths of a meter, or 10 to the negative 7th meters. At these high frequencies, though, you do find high energy, because energy is directly proportional to frequency. It turns out that the rotational vibration frequency of water molecules matches the frequency of microwaves. Thus, when microwaves strike water molecules, they resonate with the water's rotational frequency. This makes the water molecules shake faster, and thus heat up. Back during World War II, Navy shipmates noticed that when they stood in front of radar dishes, and radar uses microwave frequencies, they felt warmer. But after spending some time near the dish, they began to have trouble with vision, and some went blind. It was discovered that the liquid in the eyeballs of the shipmen got too warm, and the retinas in the back of the eyes began to detach. That is why we block microwave radiation in microwave ovens. It's not that the frequency is too high, but that it matches the rotational frequency of water. And that's great for heating food because all food contains water, but it's not so good for our eyes. In the next video, we'll investigate further the relationship between energy and electromagnetic frequencies, and we'll see how electrons create electromagnetic radiation.